Hello friends, welcome back. Today we are going to see a topic which is named as signal representation in terms of impulse function. This is a very basic topic and many times this comes across that x of n is represented in terms of del of n or shifted versions of del of n, and we keep on thinking that why it is done, how it is done. So we are going to learn this simple topic today. It is very easy and it is very important. Okay. So we'll start from a simple number system, how we write a number. Suppose we take a number 542. So how we write that number? How we split 5 into 100 plus 4 into 10 plus 2 into 1. Okay. So we split this number like this and make a total, and this is 542. So we're representing this 542 here in terms of this. Okay. So this is nothing but 10 raised to 2, 10 raised to 1, 10 raised to 0. Okay. So this is base 10, and we are changing the powers to represent various positions in a number. So you can here suppose it is 0.5, so you can use 10 raised to minus 1 also. Okay, that is 0.1. So like this, we represent the number in simple base. So 10 is very easy kind of base because simply we can represent like this. So how let us see how we can represent a signal like this. I have taken a very basic signal which is having only 3 samples. Say at -1 it is -1, and it is at 0 it is amplitude is 2, and at 1 its amplitude is 1. Okay, so signal can be any signal. We are just taking as an example this signal. So I can represent it in terms of del of n. So why del of n? Del of n is a signal like this. So its amplitude is 1 at 0, and otherwise its amplitude is 0. So del of n is very basic signal. You can represent this del of n like this: 0, 0, many zeros on this side, like 1 at this 0 position, and then 0 and so much zeros on that side. So you can have shifted version of this del of n minus 1. So it is like 0, 0, 0, and this one shifted at this position. So this is a 0 position. Okay, so this is very simple to shift this signal and to observe this signal. So this can be utilized to represent the signal. For that we have to use multiplication property of the function, impulse function. So that property says that if we multiply a signal x of n with del of n minus n0, then we get the amplitude which is present at n0. So it is x of n0 into del of n minus n0. So this is the sampling property or multiplication property of impulse function. This is we are going to use here. So here I'm taking del of n. Okay, so it is 0 at all the position except 0. So when I multiply this signal with this signal, what I'm going to get? I am going to get a signal like this. So I'm writing here by observing this property. Now shift is 0, so I'm taking 0. So x of n0 will be x of 0. X of 0 del of n. So del of n minus n0, where I'm writing it del of n only. Okay. So let us multiply this. So position wise multiplication will do. Here it is amplitude is 0, at 1, at -1 this is 0, this is 1, this is also 0. Okay, at 2. So only the sample which is present at 0 is going to come here. Other samples will be made 0. So at -1 we are having 0. The amplitude at x of n is equal to 0 is 2, and here also we are going to get a 0 at 1. So this is the output when we are going to multiply x of n with del of n. Now let us see what happens. What we need to do, if you want this sample, you want to we have to shift del of n on this side. So right shift by 1. So I'll draw the signal again, x of n. Amplitude is 2, at -1 it is -1, and at 1 it is 1. Okay, so when I multiply it with del of n minus 1, its amplitude is 1, otherwise it is 0. So it is present at n is equal to 1. So when I multiply this, I'll get only this sample, other samples are made 0. Okay. So I'm drawing it exactly below that. So its amplitude is 1. So other samples are made 0. Okay. So I am writing here, it will be x of 1, because n minus n0 it is 1. So x of 1 del of n minus 1. Okay, are you getting this? This is so simple. Now just for this sample I need to multiply with a different shift version. So this signal is x of n, and I need to take a shift on left hand side. So the signal is del of n plus 1. Okay, this is the difference, only difference here. So its amplitude is 1 at -1. Otherwise it is 0. So let us multiply. Let us multiply these two. So I'll get only this sample. Other samples are made 0. So this is -1. This is 0, 0. So let us give title to that. So here it is x of n multiplied with del of n plus 1. So plus 1. So here it will become -1 del of n plus 1. Okay. So this is so simple technique. You can go for number of samples. For example, I have taken only 3 samples. Okay. So if I add these 3, I'm going to get x of n back. Let us add. So when I add this plus this plus this, I am going to get a signal which is having a magnitude like this, -1 at -1. At 0 I'm having 2, and at 1 I'm having this amplitude 1. So this is the signal x of n. This is the original signal what we have already with us, and this is obtained by adding the individual samples. So this is how, in this we got how to write these individual samples in terms of del of n and its shifted versions. So let us write this in this signal in terms of x of n multiplied with the shifted versions of del of. So in our case, we'll start from the leftmost sample. X of -1 into del of n plus 1 plus x of 0 into del of del of n. X of 1 del of n minus 1, like this. Simply we can write like this. Now once I understand this, I can write any signal, any larger signal x of n. Let us try to write. So there are so many samples starting from -infinity. So I'll start from x of -3. So here I just need to do x of n, del of n plus 3, plus x of -2 into del of n plus 2, like this, plus x of -1 into del of n plus 1, like this, plus the 0th. Now we'll come to this point, del of n plus x of plus 1 del of n minus 1. So sign is opposite here. X of 2 plus del of n minus 2, and so on. Like this we can write signal x of n. Okay, so this is we are writing every sample. So let us write in terms of a summation. Okay, x of n. So when we are writing summation, let us take k, which is varying from, say this is varying from minus infinity, okay, like this 0 1 2 3 and so on up to infinity. So k is varying from minus infinity to plus infinity, and we can write x of k, and del of n opposite sign, del of n minus k, like this. So this is how you represent x of n in terms of the shifted versions of del of n. Okay, so this is we're trying to represent a discrete time signal. So for writing a continuous time signal, we are having a continuous time signal which is having amplitudes at every instant of time, like this, every instant of time. So everywhere you have to multiply it by del of t, and you have to shift that del of t by very small fractions. So that multiplications can be many. So you need to take integration at that time. So to represent x of t in terms of uh, del of t and its shifted versions, just need to take integration. But tau is varying from minus infinity to infinity, will take x of tau, that is the amplitude at that specific moment, tau, and del of, so del of t, okay, impulse function in continuous domain. So del of t minus, now just will replace this k by tau. So this is the representation in continuous time. Okay, continuous time, and this is representation in discrete time. So this is very simple how to represent the signal in terms of shifted impulse function. Okay, and it is weighted by that specific amplitude present at that specific moment, where we are multiplying this shifted version of impulse function. So this is like impulse function is acting as a basis to represent any signal. Thank you.